Hello mathematicians, we're now going to have a look at asymptotes and then we're going to move on to a curve sketching menu. So, an asymptote is a line that a curve approaches as it heads toward infinity, it being the curve. So as the curve goes towards infinity, it approaches an asymptote. And there are three types. Horizontal, so we can approach a horizontal value either from below or above, either is a possibility. Vertical, again we can approach that from left or right, or we can have, and this is not that common, an oblique asymptote. And by not that common, I mean not that common in this course. So we will have a look at these. So the first one, if the denominator of the function goes towards 0 as x tends towards some value, and if the numerator is not 0 at that value, then the vertical line x equals a is a vertical asymptote. Now let's do that with an example and translate this into English. So we know that we're not allowed to have x equals 4. So as the values of x get closer to 4, then we're going to see that the denominator goes to 0, so that's this part. The numerator is not 0 at x equals 4, it's actually 5, and so it can never be 0. But then the vertical line x equals a is a vertical asymptote. So this is just a fancy way of telling us what we already knew, and that is that if we went to sketch up this curve, it can't exist at x equals 4. We know from the shape of it that it's a hyperbola, and it's a positive hyperbola, so it goes like this. There is actually a horizontal asymptote as well, which is the x-axis, or y equals 0, because we can never actually equal 0. We can just get closer and closer to it. So if we were sketching this curve up, apart from labelling the axes and labelling this asymptote, then probably label that point there, and that should be sufficient. So what is that point? That's the point where x equals 0, so if we put x equals 0 into this, it will be minus 5 on 4. So now we're going to talk about horizontal asymptotes, and again we'll talk mathematically and try to translate it in a moment. So if the function tends to a definite limit as x tends to either plus infinity or minus infinity, then the horizontal line y equals b is called a horizontal asymptote. And to determine the limit, if we divide top and bottom by the highest power of x in the denominator, then use the fact that 1 on x, or for that matter 1 on x squared, x cubed or whatever, tends to 0 as x approaches plus or minus infinity, we should be okay. So again, let's have a look at this in practice. Okay, so let's just start having a little think about this. We know that x is never allowed to equal 4, so we can put that vertical asymptote in straight away. We also know that when x equals 2, our y value is 0. So we're going to pass through, we're going to pass through just there, 2, 0. We also know that we're going to cut the y-axis when x equals 0, so that would be negative 2 over negative 4, which is positive a half. So we're going to cut through there at half. We're going to touch there, as we said, at 2. It's not going to exist just here. Now, if we look at this, to work out the horizontal asymptote, we want to know what happens as, and I'm going to introduce a notation here, what happens in the limit as x goes to plus infinity of x minus 2 over x minus 4. Now, you probably haven't ever seen this before, but this just means that we have to acknowledge the fact that we can never get to infinity. So by putting this sort of notation, it's saying somewhere way, way, way out, if we did ever get to infinity, what would happen? What would we get to? And our method of working out what we get to is to say, as we set up here, to divide the top and bottom by the highest power of x. Now this is not the only method, but it's one which will get us through everything in this course. So the highest power of x is x to the 1. So if we divide our x by x, that will give us 1. Our 2 by x, that gives us that. X by x gives us 1, and 4 by x gives us that. Now, we then say, well, let's assume that we are so close to infinity that it doesn't matter. That's what this limit bit means. So if we have 2 over really, really big number, whether it's infinity or not, this thing tends towards 0. So it disappears. And this thing tends towards 0. So after we have actually taken the limit as x tends to infinity, so this bit has now been done, then what we're left with is 1 over 1, or 1. So as we go towards plus infinity or minus infinity, because whether we are adding or subtracting 0 makes no difference, we're going to head closer and closer to 1. So it works out that x equals 1 is our horizontal asymptote. And our curve is going to approach it from underneath on this side, and it's going to be approaching it from above on that side. Now, how did I know that the curve was going down here and up there? Well, again, if I come back to my original equation, if I imagine putting values in which were a tiny little bit less than 4, then a tiny bit less than 4 is going to mean, around about 2 up the top, but on the bottom is where it really matters. So a tiny bit less than 4 means that my bottom will be a tiny negative number. And when I divide anything by a tiny number, I get a really large number, and if it's by a tiny negative number, I'll get a really large negative number. So I'm heading off asymptotically towards negative infinity there. And on this one, when I put in a number which is a little bit bigger than 4, then my bottom line here is a tiny positive number. My top line is not tiny. So I end up shooting off towards positive infinity. And likewise, we've got our horizontal asymptote from our proof just here. So this is what our curve looks like. Now when we have a look at this other curve here, we could factorize the top, but we would get x minus root 2, x plus root 2. We don't get anything that cancels. So we look at it and we say, well, yeah, we can't have x equal to 4, just as on the previous curve. Now, to investigate whether there is a horizontal asymptote, if we use our technique from previously, that we take the limit as x tends to either plus or minus infinity of this thing, then we divide every term top and bottom by the highest power of x, which is x squared. So that equals the limit as x tends to infinity of x squared on x squared, which is 1, minus 2 on x squared, over 1 on x, and minus 4 on x squared. So as x tends to infinity, this tends towards 0, this tends towards 0, this tends towards 0. So we've got 1 on 0, which is not allowed. So there is no horizontal asymptote for this curve. So what does it actually do? Well, it will be an oblique asymptote, but we don't need to know how or why at the moment. So this curve goes something like this, for what it's worth. Vaguely like that. For those of you who push on with extension 2, or even after we have a little bit of calculus, you'll be able to do these curves. But for the moment, all we have to do is be able to find vertical asymptotes, which are easy, horizontal asymptotes if they exist by this process of finding the limit, and as yet we don't have to worry about oblique asymptotes. So, can we put together everything that we've learnt? And believe me, when you look back on it, you have learnt, well, you have been exposed to a lot about these curves. I'm not going to be bold enough to say that you've learnt it just yet, because it takes time. It really does take time. You know, I hope that you're feeling more comfortable with the variety of curves, and it will be the same with curve sketching. With time and practice and getting more and more comfortable, you'll come up with a way that you can end up having a pretty good go at drawing most curves. And of course, if it's homework, then you can always go to GeoGebra or some curve sketching technique and double check and see whether you could work through the logic. But this is our menu, and the first step here, and this is just copied out of the textbook. There's nothing original about what's in the text on this, so it's as good as any. But what is good is this step of preparation, and the reason I bolded it is that it's really the secret. So in here, in preparing to be able to sketch the curve, make it simple. So combine any fractions that you've got using a common denominator, so they'll be algebraic fractions. Factor top and bottom as far as you can. Maybe stuff will cancel out, but remember, if it does cancel out, it doesn't mean that it's gone. It's just giving you a simpler version. We may have to come back and remember what was on the bottom for the sake of the domain. And that's why looking at the domain is really important. So the usual restrictions on the domain are there x values which we can't calculate a y value for. So zeros on the bottom, square roots of negatives, they're our two most common ones. Now the text then says symmetry next. Find whether the function is odd, even, or neither. To be honest, I wouldn't rate this step so highly. I think if you go to this one, find the intercepts, so it should always be easy to find the y-intercept. It won't always be possible for us to be able to solve to get the x-intercepts, but if we can, we should do it. And the bit that we battle with about the sign, finding where it's positive and where it's negative, you may or you may not have to do that. It'll be like a fallback situation. Vertical asymptotes, definitely, and I would probably rate these up here somewhere. And horizontal asymptotes, have a look at as well, and I'd probably stick those up there. So I would say this is the key, this one here, to get underway. While you're doing that, be aware of this. Think about the asymptotes next. Or actually probably the intercepts next, asymptotes after that. Then if you've got time, think about symmetry, and if you need to, think about sign after that. But it's going to vary depending on how easily you see the essentials of the curve. So let's look at this in practice. So for our first curve here, x minus 3 on x plus 1, and these probably should say f of x equals this or y equals this, because that's what we're plotting. We're plotting it on the xy plane. So we can see that we're not allowed to have x equals minus 1, so we've got our vertical asymptote there. We can see that when x equals 3, the value of y will be 0. So out here at 3, y is 0, so we're cutting through the axis just there. You are probably guessing that we have something looking vaguely like a hyperbola here, and that's a good guess. So think about what happens as we now shoot off towards infinity. So if we take the limit as x tends to plus infinity of x minus 3 on x plus 1, we know that that means we divide through by the highest power of x. So this will become 1 minus 3 on x over 1 plus 1 on x. So as x tends to infinity, these terms drop off and we will tend towards 1. Now, is there a way of telling if you tend from the top or the bottom? Well, there is a little bit, because we are subtracting something from this one and we are adding something to this one. So the top is going to be slightly smaller than the bottom. So we're going to come towards that one from underneath towards plus infinity. So if we put our asymptote of +1 in here, we know we're passing through this point, so we're going to be heading off, coming underneath just there. And over the other side, as we head to minus infinity, so I'm not going to rewrite all this, but as we head to minus infinity, then again, we will be subtracting a really tiny negative number, but subtracting the negative adds to 1, whereas subtracting the negative down here subtracts from 1. So what I'm trying to say as I stumble around it is that this thing means that we will be coming towards the asymptote from above, like a value a little bit more than 1. So we're heading towards 1, but we're coming from the positive side of it. Now your understanding is probably pretty good at this stage that if I also find the point, which I neglected to do earlier on, where we cut the y-axis is where x equals 0, so that will be at -3, then we're going to go down like that, because as we get closer and closer to -1, when we're a little bit less than -1, this number is going to be a tiny positive number, but our number up the top will be a negative. So we'll end up with a big negative value, so that's why we shoot on down towards minus infinity. And likewise, when we are -1.0001, our bottom is going to be a negative, our top will be a negative, but the bottom is tiny, so we're going to shoot off towards plus infinity that way. Now, I think this is probably as much as we need to worry about with our graph, and that's a pretty good sketch as far as we're concerned. Now, before I leave this all together, I might just add a little bit, which could be a nicer way for some of you to think about it. Don't feel that you have to. And if you do extension 2, it's also a nice little trick. I could take my x minus 3 and x plus 1 and break that up. So I could make it an x plus a 1 minus a 4. Okay, so that's still x minus 3. Put that all over x plus 1. And then I could write that as x plus 1 on x plus 1 minus 4 on x plus 1. And this, of course, is 1. And that gives me my horizontal asymptote as well, that value just there. It's called the method of partial fractions, which is, as I said, beyond the course, but it's not hard, and it's something you may wish to have in the background somewhere. Okay, let's look at our other curve. Now, with our other curve, we could be tempted to think that this is quite a hard curve to do, but if we do that preparation, it might make life easier. And it's only because the preparation does actually let us do some cancelling. So if we look at the top line here, it's a quadratic which would factorise to be x minus 3 x plus 1 over x plus 1. And we can see that that x plus 1 cancels out. So really our curve is just y equals x minus 3. But we have a little caveat here that it is y equals x minus 3, which is cutting at minus 3, has a slope of 1, so it also cuts at plus 3. But what we did here when we simplified algebraically was that we lost some information. And the information we lost was that the curve is not allowed to exist at x equals minus 1. So out here at x equals minus 1, this curve actually has a little hole in it. It just doesn't exist. So I meant to draw it, I have to draw it up with that hole there. Like ideally it wouldn't have that line in the middle of it, it would just show a hole, but I can't easily rub that out here. And that's the resultant curve there. X squared minus 2x minus 3 over x plus 1 is the straight line but with the hole in it. Now if you in extension 1 are given one of these, that will be the sort that it is. The ones with the oblique asymptote end up turning up more in extension 2. So graphs with a hole in it, possibility. Most graph plotting programs, by the way, can't cope with this. They don't do it with a hole in it. So have a go at these, then breathe a sigh of relief because we're finished with trying to draw fancy graphs for quite a while.